Great. Good afternoon, ladies and gentlemen, and please welcome our newest engineering seminar at CBK PAN. Today's guest and lecturer is our unique colleague from CBK PAN, Professor Władysław Kofman. I'm very sorry. And the lecturer is, forgive me, I got some type of problems with my computer. And the lecture name is Radar Techniques Applied to Planetary Subsurface Studies. Well, it seems extremely important and interesting, especially that our lecturer, Professor Władysław Kofman, is a very distinguished physicist, astronomer, and engineer. He is currently a research director emeritus at the Institute of Planetology and Astrophysics de Grenoble, and a professor at the CPK PAN. Professor Kofman has made significant contribution to the study of planetary surfaces and subsurfaces, Earth's high atmosphere and ionosphere, rather remote sensing and signal processing. He was a principal investigator at the concept experiment for the Rosetta mission. He has been involved in various ESA, NASA, and JAXA space missions. He has held several visiting professorships and advisory roles through his career, including at Cornell University, University of Nagoya, the Max Planck Institute, Polytechnic, and the University of Western Ontario, and the Jet Propulsion Laboratory at Caltech. He has received numerous honors, including being named a Cavalier of the French Legion of Honor and honorary fellow of the Royal Academical Society. And one more thing that seems very fun, but also unique and incredible. The asteroid 13368 was named Władysław Kofman in our professor's honor. So I give the voice to Professor Kofman, and I'm waiting for a unique and wonderful seminar.
Thank you very much for this nice presentation. Okay, I will tell you today about the radar techniques which we apply for the subsurface studies. In fact, the radar techniques started to develop in general after the Second World War, and to develop, and is used now permanently everywhere, I would say. But the use of the radar technique as the penetrator below the surface to study the subsurface started, in fact, mid of 80s, beginning of 90s. And then we have some proposals which now are on Mars, and this technique started to be really accepted, because at the beginning, I remember the discussion we had in 93, 95, with specialists, we were told we will never detect anything below the surface, because it will be really perturbated by surface, etc. And then, in fact, it's not true. Today I will explain you how the radar works. It will be rather general, but there is some special things for the sounding radar. And I will not talk about the military radar here. Then we are talking about the sounding radars for science, let's say. And on some observations by Marsis radar and Charat radar on Mars, I will show you some results, discuss them, and talk a little about the future missions. Okay, here you will just see two missions which are now on Mars. One is Mars Express, another is Mars Reconnaissance Orbiter. And on these two radar, we have, or the missions, we have two radars. One is Marsis here. The antenna is very big, it's 40 meters antenna. And here there is Charat radar, which has smaller antenna of 10 meters. And these radar are working since 20 years, one can say. And it is why, because a radar is a really efficient method to go to the interior of the solar system object. It works, it signal responds to the changes in the electric properties, which means that if you have some layering with different electric properties, we observe. We can measure the detection on this, scattering, and the reflection of electromagnetic wave. And this is the principle of the radar. You can see here how the nadir-looking radar works. This is the surface of the planet, and radar is looking down. And you have two, let's say, different properties of this, which can be good and bad. We have the signal coming from the same distance on the Earth, arrive at the same time, which means that we send the impulse, which are reflected by this part, of surface and that one, and there is reflection at the same time, which means that we have to find some way of distinguish this and discriminate this fact, because the signal at the same time, a signal coming from below the surface, which means that whole reflection from the surface is perturbated by, let's inverse, the reflection from the subsurface is perturbated by the surface reflection. And we have in some way to eliminate this, to discriminate this. This is now the processing of the signal on the surface. We have the processing along track, which means that you use the SAR technique. I will talk a little about after. And this is, of course, done by antenna. We have two way of separate, and across track, the satellite is moving in this direction, and across to this direction is defined by antenna pattern and by pulse limited observations. I will go back to this. But the question really to process the data, we need to simulate the echo coming from the surface. When I'm saying to simulate the echo coming to the surface, it is done in order to discriminate, separate the echo from the subsurface and echo from the surface. It's one way and probably more efficient of doing this. Okay, let's see, this is very short image. We send the pulse radar, which is reflected by the ground and transmitted below the surface. Then the reflection from the ground arrive at this moment, but the signal propagate inside and will be reflected by second layer, if there is any, inside. Then this signal arrive at time T2 to the receiver. And then signal propagate down, and we can have many reflections like that. And we have used it in order to interpret the data. And of course, this I am showing very simplified schematic, which shows the reflection on the layers. But we have of course, the scattering on the roughness inside, on the blobs, on this kind of thing. This arrive also to the receiver. This can be seen as noise perturbating the data. Okay, here you have different type of the reflection, is specular reflections, when the surface is flat or relatively flat. Then we have the surface scattering, and the scattering is on the irregularities on the surface. The signal propagate inside, going back, and all these processes are well, which means that we should do something in order to interpret correctly the data. Let's go. Main radar parameters are firstly range resolution. The range resolution the resolution is defined as the separation between two signals which we can distinguish. But also the resolution include if you have volume, if the signal coming from the volume, the resolution defines the volume from which we see the signal coming. It's important. For simple impulse, the resolution is given by this formula, is the velocity of the light, which is different inside the medium than in the air, and duration of the signal. Or for the modulated signal, as you can see, is divided by the bandwidth of the signal. Modulated signal, very often you have linear modulation of frequency, which means that signal is very long, but inside we are covering a wide band. Then what we call the resolution after compression. Compression means it's the operation in which we correlate the incoming signal with the copy of the transmitted signal. And then it's in fact autocorrelation of the transmitted signal in the simplest case. And this makes the signal is very, after this correlation is very narrow. It depends on the bandwidth. And it is the reason why for this kind of radar, and not only for all military radar, is that the people use the modulated signal. Okay, now, sorry. Cross-track resolution, as I told you, depends on the antenna or on the duration of the impulse. Of course, the resolution along the orbit, along the movement, is defined by the SAR processing. But the resolution over the across depends on the roughness of the surface, then it can be time limited, or it's depending on the first Fresnel zone. If you have a flat region, then you have coherent answer of the surface. Then the signal is penetrating inside the medium and it's absorbed. The absorption, attenuation in dB per meter, this is the formula, depends on the electric constant, of course, on frequency, and on loss tangent. Shortly, loss tangent depends on the conductivity in the medium. If you have a large conductivity, the loss tangent will be very big, etc. And you have here some materials which I am showing. Firstly, the real part, okay, I did not say, the electric constant is constituted from the real part and imaginary part. The imaginary part is the conductivity, let's say. The real part is the part which determines the speed in the middle, speed of wave in the medium. Is an approximation, because when the imaginary part is big, then it's not so simple. Okay? And you have some number, what I show here, of the electric constant, because on the surface of the planets, we have volcanic rocks, we have ice, a lot of ice, as you will see. We have the CO2 ice, and brine, basaltic rocks, different type of things. And here you have the value which we have for this kind of material. What is important to see here that for materials, what I showed here, the loss tangent is low. It's 10 to minus 2, 10 to minus 3. Of course, for brine, it's not true, because the brine are very conductive. And this is important for the penetration of the radar. When you see the formula here, which is attenuation in the dB per meter, it's proportional to frequency, which means that for us, the best things in order to penetrate below the surface is to use the lowest frequency as possible. It's not always possible because if you want to put 40 meters antenna on the spacecraft, the ESA or NASA will take you, no, we don't like this, because it's very big. And it happened for Marsis, but for Sharat, it was much smaller. And you will see that for the next generation of radar, we have the smaller, because it's hard to build this kind of big antenna and send in the space. Here is to show you the numbers, the loss for dB per kilometer for frequency of 10 megahertz, radar at 10 megahertz, and here is 100 megahertz. And you see different type of soil. We have sand soil, the losses are 10 dB per kilometer. 10 dB is nothing. We can easily have 40, 50, even 60 dB of dynamic to go down, but which means that for Landescent with 10 megahertz, we can go, in fact, until all this material we can observe easily at 10 megahertz, which means I am saying observe, it's penetrate inside the medium. Here, or 100 megahertz, it's no way, which means that you see the limit. For low frequency, we can go let's say 5 kilometers below the surface. It happened, I will show you the results. For higher frequency, we have to stop at meters, perhaps tens of meters, but not more, because we have which really depends on material. For ice, it's a better situation. For pure ice, it depends on the structure of ice, but normally what is important to see here, that for frequencies, low frequencies, from 1 megahertz to, let's say, 100 megahertz for ice, the electric constant is about 3.2, 3.1, and attenuation is very low for a large number of temperature. You can see here that we have few dB attenuation per kilometer, which means it's nothing. Then if we have an ice, we can penetrate very deep in the ice. And this is the case on Mars, when you have the polar cap, and we have the big polar cap, north and south. And we penetrate there up to 5-6 kilometers to go to the bedrock. Okay, now let's go for the process. How to do it? Normally, the goal of course, the process is to, if you are in this situation, then we have the surface answer here, and here we have a small echo coming from the subsurface. Then the processing should be able to increase the signal-to-noise ratio. This is not necessarily noise. This can be the reflection from the surface. And in order to obtain increased signal-to-noise ratio, and to see this echo coming from this is the objective of processing, of course, and to see there are the direct processing of the data time by time, and come back, or we can plot and process all the images. And this increases our capacity also to detect the layers. Okay, well, let's see how it works, the measurements, short film. We have the Sharat radar flying over the Mars. It will be over the polar cap, in fact, you see. And the signal is sent with repetition of a few milliseconds. It's penetrating to the polar cap, which is on the image. And you will see what we call the profile. This is, as you see, this is the profile across the polar cap. You see the surface, and you can see the things under the surface. And this is way how we present the data. We present it the way that you have what you call fast time with depth, which is of the order of microsecond. when the signal propagates inside, it's coming back. And you have the slow time here, which is a time of signal repetition, which can be milliseconds, tens of milliseconds. It depends on how radar is working. And we show what we call the radargram. This is short time, and this is slow time, which means that satellite is moving on the orbit and taking the data, which we present in this form: fast time, slow time. Okay, going back to the radar we have today. It's a radar which was sent on Mars Express in 2003, but the radar antenna was open in 2005, because after accepting the mission, ESA started to be afraid by the antenna. And they did not want, they asked us to make studies and studies and studies to show that that antenna can open and it will not kill the mission. It's understated, but it should be done before. But anyway, it was open in 2005. Still 2005, the radar is still operating. And there is a Sharat radar on the MRO mission, was open in September 2006. It's still working very well. The differences in radars are, first difference is the bandwidth. Here, the bandwidth is of 10 megahertz. It's not written, but the bandwidth ±5, yes, it's written. 10 megahertz bandwidth around the 20 megahertz on Sharat. On Marsis, we have four frequencies operating with bound of 1 megahertz. And the bound, as I told before, defines the resolution. And the resolution for Marsis is 70 meters, because the bound is 1 megahertz. And for Sharat, it's 7 meters, which means that we are seeing the things below the surface with the resolution of the order of 70 meters for Marsis and 7 to 10 meters for Sharat. Much better resolution. But the frequency being 4 times larger, the penetration is much smaller. On Marsis, you penetrate up to 5 kilometers below the surface. On Sharat, it's only 1.5 kilometers, which is difference. But what happened with Sharat is that they recalculate the lobe of antenna relatively recently, and they found that the rolling spacecraft, we can obtain larger signal to noise ratio. And it's now used, but it took some time. Okay. And the space resolution along the orbit, which means that after SAR processing, is of the order of 300 meters for Sharat and of the whole kilometric order for Mars. Now, going back to the problems. All the institute studied a lot of ionosphere for many, many years. And the signal propagating through ionosphere is dispersed, is distorted. And when you send the signal from above from 800 kilometers over the surface, the signal goes through the ionosphere of Mars. And the ionosphere of Mars is a little comparable to the E region of ionosphere Earth. Then the signal is distorted, is attenuated, and it's some kind of, it's a Faraday rotation also, which means that we have to take into account this kind of things. What we are doing is, you can see the signal without ionospheric correction, and the dispersion of the signal time is seen here. This is due to ionosphere. This This skip is different due to the different type of operation, before, before, but doesn't. But this kind of signal, dispersion and the lead distortion, of course, is due to ionosphere. This we should also correct. Is done, and this product of the correction is total electron content, which means that the radar, which was built to study the subsurface, it appeared that we can study also the ionosphere. It's done now systematically. And this is total electron content depending on the activity of the sun, the color connect to the activity of the sun. But we run for each new orbits, we have to determine a correct ionosphere, and then we have a subproduct total electron content. Then the main problem, in order to analyze the data, as I told, is to correct, determine the influence of the surface reflection. Because the surface reflection will perturbate our signal coming from the below. And this we are doing by the, let's say, deterministic simulation of the signal, which is reflected by the surface. But in order to do this, we have to have the model of the surface, the digital model of the surface. And for Mars, we have this kind of model. It's the MOLA model, which covers completely the planet Mars with the resolution of 100 meters, 200, 300 meters. And with the new observations, not new, but in the time, we have the digital models with the resolution of tens of meters, with the camera now flying on different missions, which means that we can do very precise calculation of the signal reflected by the surface. I compare this with the signal observed by the radar. We use the facet mode, which we developed, let's say, many years ago, in which each surface is represented as facets, rectangular or triangular facets. It's better triangular facets. And this accelerates the calculation of the reflection, of course. We use this method. This is, for instance, the MOLA, the topography obtained by MOLA. We use this kind of models, in fact, to describe our measurements for each orbit. And how it works, this is whole system of the signal processing. It's some schematic. In red, we have the input, which means that there is emission scenarios, which means orbit, trajectory. We use this in different frames, in the frame of the object observed, and to see how we eliminate the surface. This is the problem. Then we need to have instrument module, which describe the process in the processing inside the instrument module. This is signal processing inside. And target model, what I said, digital model of the terrain. Then we do all calculations, and we calculate the signal coming from the surface. And now even we calculate the signal coming from the subsurface, but this is more complicated. And then we compare this calculation with measurements and interpret the data. It looks like this. Oh no, cell synthesis. For cell synthesis, I don't know, probably you know it about different application. In fact, what happened when satellite is moving on the orbit here, and we have here the reflection point. This point, the distance to this point will change from the longest distance, the shorter, and to go back. This describes some of parabolas due to the change of the distance. this change of the distance also appears as phase modulation on the received signal. And in SAR processing, we will correct this kind of parabola inside the SAR processing for each point on the surface. And here are the measurements before the correction. And you can see some parabola appearing here, which is a real signal from Charlotte. Then these are Charlotte measurements from the previous example. This is the SAR synthesis for Charlotte data. You can see that this kind of parabol disappear and you have the signal like that. This is the surface signal. And all this echo you see here, it's not a subsurface, it's a surface. And then this is the range compressed signal. I explain you what mean compressed. Is the correlation with the transmitted signal. And then this is SAR synthesis of Charlotte data. Here, it's something disappear. Okay. Well, let's go here. And these are to show you the simulations. It was previously it was the measurements. So here we have the measurements. And on this slide, there are the simulations. This is the output of our simulation. You see perfectly well the existing parabolas, etc. And we made the SAR synthesis on the simulations. And you see here the Charlotte measurements, which compare very well. It's of course not one-to-one. There is no way because we don't know so well the surface. But it's clear that the depth, large depth, the reconstruction is very good. As you will see here, these are the measurements of marshes over the polar cap. And here we have the simulations. You can see that this kind of echo here, seen here, is the surface. It's not subsurface. It appears and subsurface because it derives to the receiver with this kind of delay. And but these are the surface echo. But here you can see this continuous line, and this is subsurface echo. This comes from the subsurface of this polar cap. And this is topography of the region below the satellite. Here there are some measurements of the north polar cap. You can see that these are the Charlotte measurements. You can see that we penetrate here up to 1.5 kilometers. And you see some layers below. And this, we can have two presentations. One presentation is time, delay time, which we are measuring. The radar is measuring the time of propagation. And then we have to have the knowledge of the dielectric constant. And we correct by speed inside the body. You have these two images, one is time and one is distance. And this is different radargram, but obtained with marshes. We can see that you can go here on the south polar cap, 3 kilometers below the surface. This is the ice. The Charlotte did not reach this depth. Bon, now these are the marshes observation. I will show you the short film. What we see here is different region below the surface in the polar cap, the north polar cap. This is the orbit. This is the trace. The line, the white line is the trace of the antenna lobe on surface. projected on surface. And this is the echo coming to the radar. There are different units, and here is the same region, invert time, obtained by Sharat. You see that Sharat resolution is much finer, and then you can see very, very good layering. Then here it's in different region, which is important. In the low latitudes, we can detect the ice. As you probably know, there are the plans to go to Mars. And I don't know, there are people are saying a few years, 10 years. I don't believe that we'll go before 50 years. But okay, there is a lot of mission now in order to determine where is the ice, in order to produce the water when the people, and we have to really do the mapping, complete mapping of the ice on the surface. Anyway, here is the detection of glaciers in the mid-latitude. This is the glacier in the mid. This kind of study is possible, but not only. These are the direct observation. We can interpret this in different way, but here we observed in part of Mars. In part of Mars, we measured this part of the polar cap, and we were able to rebuild the subsurface from the behavior of the topography of the Mars. And from this, we defined the depth of the ice polar cap. And from this, we were able to determine the dielectric constant of the medium. You can see here, we have epsilon here, which means the real part of the electric constant, and loss time. And what is clear in this part of Mars, that you have a really pure ice, because the absorption is very, very low. See, loss tangents is 10 to the -3 of the order this, and which means that there is almost no attenuation. And the ice has 3.1 dielectric constant, which will real part. Then, these are some other measurements, just to show you the difference between Sharat and Mars. If you want to study very narrow layering inside, below the surface, you should use the wideband radar, like Sharat, which is 10 megahertz, and Mars is much less. But of course, then you have the problem with penetration. Okay, here you will see we reconstruct three-dimensional polar cap using different orbits. The white lines you can see here are the trace of the orbits on the surface, and the measurements are above. And from this is using all this data around the polar cap, we were able to build a polar cap below the surface. You have here, and we have maximum thickness of 3.7 kilometers. It's a big volume, it's 10 to 6 cubic kilometer of ice on the polar cap, which will give equivalent water of the order for 11 meters. If you distribute this water over the whole globe, Mars, it will be 11 meters of water. Then another thing what you can do is to determine the reflectivity of the surface. The reflectivity of the surface, if you can normalize things correctly, give us the possibility to determine the dielectric properties of the whole surface of Mars. And this was done with Mars data. And here we have even because Polish, I wrote this for students here, I think, is these are the measurements. This is a real dielectric path. You see that the whole north and south is in blue and green, which means these are the low dielectric constant. The low means that there is probably water ice there. And this is, here is compared with the, how to say it, there are the instruments measuring the abundance of hydrogen in the first meters of the subsurface. And this is how many water equivalent, it's not really water, it's the presence of hydrogen in the mineralogy of Mars. And you have plenty of water in the north and here also, which correlate well with the electric properties which we determine, which shows that in the North Plain, not only, we have a lot of water, ice, like in permafrost inside like the permafrost. This is different presentation of resin. All this region to the north has very low dielectric constant, which means that we have most probably here a lot of water ice. It's really permafrost. And this is fine because this correlates with the shorelines of the putative ocean which exists on Mars. I don't know if it's because there are large discussion about this, if really the ocean, this is the shoreline, this line is the shoreline of the putative ocean, which englobe well our measurements. Oh, going faster. And these are a different type of measurements in this equatorial zone, in which we can detect also the presence of subsurface. And we don't know really if this is the ice or not, but we detect some layering. And this is in different parts of the Mars also, on different orbits. Then we observe a very long line of subsurface. And this is most probably the ice-rich region. And on the polar region, it's certainly ice. Here, it's probably ice. And here, we really don't know. This kind of study one can do, and I will finish with another elite controversial presentation paper, which was published in Science in 2018, in which we observe very strong echo coming from very relatively narrow region. And to interpret this echo coming from the narrow region, from below the surface, this is the surface, this is the echoes coming from the below the surface, this can be interpreted, it was interpreted as the signal reflected by the water, because the dielectric constant determined here are about 20. Perhaps this will be easier to see. Even going to 40. This kind of dielectric properties, the only things to interpret this is to say that it's the liquid water. But liquid water at 1.5 kilometers below the surface, for the people doing the heat calculation, this kind of thing, is not possible. Which means that still we have a discussion how to interpret this. We proposed different type of interpretation because we discover recently that there is a blanket, small layer on the surface in this area here, due to the volcanic explosion and craters from previous history. And if it's the case, really, it was observed by camera, then we can interpret this signal differently because it's due to this layering. But anyway, it's not decided. Of course, it's very controversial. Now, in order to finish, okay, it's not finished, the story, because the radar running on Mars show to our agencies and to the people that it works. Then to go for on Jewish mission, to go to Ganymede or to Jupiter, and on mission of Europa Clipper American, which was just launched a few months ago, we have a radar. We have two radar. One is the Rhine, which was built by Italians, and this radar is close to what I would say Marsis, because it has the central frequency of 9 megahertz. Bandwidth rather narrow because 1 megahertz bandwidth, 1 to 3 megahertz bandwidth, but is the Marsis was used, and Marsis and Charlotte was used as prototype really for this Rhine radar. Some improvement. And there is another radar on the Europa Clipper mission. In fact, two radars. There is a low frequency radar. Here you can see the antennas here, two antennas, two dipoles. And this is 9 megahertz radar with a small bandwidth, also of 1 megahertz. And here you see the antenna of VHF radar, which is at a much higher frequency, which is 60 megahertz. And then this radar was built by Lancashire in Arizona, and JPL is multi-frequencies, and it will give additional information, especially during the close subsurface region, close to the surface regions. Okay, I think that I will stop here. Thank you for hearing. Keep my time, 45 minutes.
All right, thank you very much, Professor. Are there any questions from the audience?
Because you show a lot of thank you. You show a lot of way to compensate the data, analyze it, post-production. How much of this compensation is made on board on the spacecraft, and what is sent spacecraft?
On board of the spacecraft, there is the data compression, but we can transmit the raw data also without doing anything. But normally it's the signal compression. You mean time compression, not SAR processing. SAR processing is done on the Earth. And there are some accumulations that can be planned. How much? Depends on repetition, but let's say 4 to 30 accumulations of the signal, direct integration of this. So, of course, you have to calculate the opening of the windows and this kind of thing, but this is to operate the radar, because you cannot perceive because there is no mirror, which means that you open the window given time of reception and you send this to the Earth.
Okay, thank you.
Okay, rather technical question. What kind of power do you need to produce a signal like that? And how do you accumulate that energy?
We don't need too much power because the transmission is of the order of few watts. 10 watts. There was one radar which was sent on the moon. It was sent cylinder radar, which was sent by our Japanese colleague. I worked on this, but they sent a half of kilowatt. But we don't need this. Of course, we need the signal to penetrate, etc. But the problem is that the clutters, what you call the clutter, is the signal coming from the surface, increase in the same way, which means that the signal to noise ratio, the noise ratio coming from outside, let's say, then galactic noise is increasing when you increase the signal. But signal to clutter noise is not, because the clutters are directly connected to power of your signal. Which means that this is but a radar like Mars is 10 watt. And Rhine also will the order. And we use the batteries to charge.
Okay, one more. This one will be rather tough on you. Talking of geopolitical situation and things like that, can you imagine any uses of sounding radar for Earth observation purposes on drones? Would that be efficient?
There is Sentinel mission, which is in some way also can penetrate, but not too much, only a few meters, or on ice perhaps more, but it's different things. And the problem with this sounding radar at 10 megahertz, this kind of thing, is ionosphere. As I show you, the ionosphere dispersed and perturbate the signal, and we have to correct this. If not, we cannot use the Mars data. For Charlotte, it's a little better because it's higher frequency, but it's still need the corrections, which means that for Earth, low frequency radar, it's a problem. This is, but SAR radar, you have all the time operate. There is a question there. No question.
No questions? Okay, I don't see any questions on chat.
One moment. Okay, Nata.
One question. It is interesting for me. What is exactly under the Meridiani Planum? But it is a problem with interpretation rather data. Yes.
And you see this here, these are two orbits which are close, A and B. These two orbits are close, and you see the measurements. And you see just very narrow, small line here, disappearing in the sense because the topography changes. Which means that this is, we don't know what it is.
It is not ice, rather.
Probably not.
No.
I'm saying probably, or not. We don't know. It's the paper of GRL.
But I remember some years ago, and professor said that it is maybe very thin sand.
Maybe.
Okay.
Maybe, because you know, the penetration it's not very deep, close to the surface. It's possible. We observe these things, but to interpret it's not so obvious.
Okay, we will see. Thank you.
Right. All right. So thank you very much, Professor. It was a wonderful lecture. I hope we're gonna go back to that subject on some point at our seminars. So thank you very much for today's lecture.
Thank you.